let's talk about the solution formation process, which is the dissolving process. Let's look at what has to happen when solid particles are dissolved in a solvent. So what I'm going to do is that I'm going to draw a beaker here. I'm going to place some solid here. You can consider it as sugar or salt, a solid. All right. I'm going to add some solvent here. Let's say it's water. First of all, we understand that only the particles on the surface of the solid can get dissolved. All right, now let's look at one particle here. Let's assume this is the particle we're looking at on the surface of the solid. Let's look at what has to happen for it to get dissolved in the solvent. First of all, when this particle is staying on the surface, it is attracted to the other molecules of the solute around it. So in order for this one to get dissolved into water, it has to overcome the attractions between this particle and other solute particles around it. Does it make sense to you? So it has to overcome the interaction between the solute and the solute particles. It has to overcome the attraction between this particle and other solute particles around it. Number one. Number two, for this particle goes into the solvent, for example, it stays here. Now, before this particle comes here, there are water molecules here that are attracting to each other. In order for this particle to come in the solvent, it has to break the attractions between these two water molecules. Does that make sense to you? So for solid particles to get dissolved, it has to overcome the attraction between solvent and solvent particles. Okay, let me erase some of this. Okay, so if there's a water here, there's water here. For this particle to come in and stay between, it has to break that interaction between water and water molecules, which is solvent. So for solid particles to get dissolved, there are two types of interparticle attractions must be overcome. Number one, the attraction between the solid particles. Okay. Number two, the attraction between the solvent particles so that the solid can stay in between them. If these are the only two things that are happening during the dissolving process, nothing will get dissolved because both processes need energy. Luckily, there's a third kind of interaction, a new interaction that is formed. For example, I'm going to draw it from beginning again. Let's look at this particle on the surface again. Right now, once you add a solvent to the beaker, on the surface exterior of this particle, there are tons of water molecules. These water molecules will start to interact with this solid particle. If this interaction is strong enough, if this attraction is strong enough, these water molecules will work together to pull it away from the solid surface. So once you mixed a solid and solvent substances together, there is a new type of interaction forms. That is attraction between the solute and the solvent particles. And that is the driving force for dissolving. Whether something will be dissolved in the solvent or not is primarily decided by this interaction. If these solute particles and these solvent particles, if they like each other, those solvent particles will grab the solute and burn it into the solvent to dissolve it. If they don't like each other, if they have no communication between them, then it is not going to be soluble. We're going to look at the details of this in the later episodes. Once you have some solute particles dissolved in the solution formed, now there will be two processes going on. Number one, some of the particles on the surface of the solute are still get dissolved, and some of the particles in the solution already, they may come back to deposit on the surface of the solute particles. So there are two processes going on. Some of the particles are dissolving, some of the particles are coming back to the surface of the solid. At a certain point, they will reach an equilibrium, and you are going. At that point, the solution is saturated. Again, dissolving is a dynamic process. Now let's talk about the factors affecting the rate of dissolving, the rate of solution formation. If we understand what's going on in the process of dissolving that we discussed on the last slide, you will understand everything on this slide. So first of all, the state of subdivision. The greater the surface area, the faster dissolving. Pretty straightforward. Greater surface area, more particles are on the surface of the solute, more likely they will get dissolved. So that's very straightforward. Number two, agitation. Stirring something, shaking something can make a solution forms faster. Why is that? Well, think about this. Let's have either a beaker or a cup. We place some sugar in here, and we add some water. Our goal is to let the sugar dissolve. If we keep the staying here, not disturb it, what will happen given time is that the molecules on the surface keep dissolving, and in the surface area very close to the solid, there will be lots of sugar particles. Going away, farther away, you have less and less sugar particles. If it is not disturbed. Does that make sense to you? Yep. So given time, there will be tons of a lot more particles right around the surface area of the solid. Farther away from the surface area, less particles. When you have a lot of sugar particles right around the surface area of the solute, two things are happening. Now, number one, you have more chance for these particles right around the surface area. You have more chance for them to come back to deposit on the surface of the solute. So they will come back from the solution. That's the opposite process of dissolving. That will make dissolving slow. Does it make sense to you? Now the second process is that, remember on the last slide, we said that the interaction between solvent and solute particles is the driving force of dissolving. If you have a lot of sugar particles right around here, you are reducing the interaction between solute particles on the surface and the solvent particles. Does that make sense to you? Many solvent particles at the surface area are replaced by the sugar particles or solid particles. Therefore, if you don't disturb it, there's no agitation, there's no stirring. Given time, there will be less and less solvent particles around the surface area of the solute. So there will be less and less interaction between solvent and solute particles, which is the driving force of dissolving. Therefore, agitation will make a dissolving faster, because when you shake it, stir it, then many of these particles are removed. Many of these particles are removed away from the surface area. It goes away. So you're increasing the interaction between the solute and the solvent. Also, you're reducing the possibility for the solid particles to deposit back to the solid surface. Number 3, temperature. Higher temperature, faster dissolving. Why is that? Well, this is relatively easier because we learned that on the last slide, in order for the solid particles to get dissolved, it has to overcome the attraction between the solid particles. How to overcome that attraction? Higher temperature, higher kinetic energy. The higher the temperature, the higher the energy the particles have. Those particles can overcome the attraction and move into the solvent particles. So those are the 3 factors affecting the rate of dissolving. Number 1, surface area. The greater the surface area, the faster dissolving because only the molecules on the surface can get dissolved. Number 2, the degree of agitation. Basically, agitation increases the possibility of the solvent and solid interaction. It moves the particles on the surface of the solid away. Number 3, higher temperature, faster dissolving. Higher temperature, higher kinetic energy, easier to overcome the attraction between the solid particles. See you next time.